This lecture is being brought to you in part by the generous gifts of these sponsors.
Thanks very much, Ken, for that very warm, generous introduction. It is great to be back here in Pensacola. It has been too long. When we left Denver yesterday morning, it was 6 below zero. Nice change in climate here for us. My wife and I are enjoying this very much. We thank you for your hospitality. You know, this is a great time to be talking about our future in space because NASA is getting ready to launch a new era of space exploration with new rockets, the Space Launch System, new space vehicles, the Orion, that will take us beyond low Earth orbit for the first time in almost 50 years. The last time any human left Earth orbit was December of 1972. That was the end of Apollo. That was Apollo 17. Dr. Jack Schmitt, who's visited here a number of times, was one of the astronauts on board. We have not left Earth orbit since then. We stopped exploring. And so it's well past time to return to those adventures of space exploration. And what we're going to do today is we're going to talk about what there is to explore. We're going to talk about, first and foremost, why do we explore space? Because the reasons today are dramatically different than in the 1960s when we first took those steps off of Earth and went to the moon. And it's a different dynamic. It's not just the United States against Russia, but we have many other countries that are very active in the space program and companies. We saw some exciting launch just 2 weeks ago, SpaceX and the new Falcon Heavy. Those are major players now. So the whole climate, the whole environment has changed. So it's an exciting time to look at it. And so I'm going to start off asking the question why we explore. Then we're going to pursue some of the new technologies that are used for exploration and space launches. And also, what are the places to visit? Certainly getting back to the moon, because we only touched on during Apollo some of the most interesting things to be done to the moon, but there's Mars and then beyond. So we want to cover all of those. The other thing that's exciting too about the, let's see, this laser pointer, I think that we've got, let me see, here we go. Coupled with the new technologies is a new methodology for exploring that combines humans, robots, and even telescopes, which are exploring together. So we're going to hit that all and bring this technology piece into this development. So let's flash back to the 1960s. And the first time we went exploring, it was the middle of the Cold War, and President Kennedy stepped up originally in 1961, just weeks after Alan Shepard has made his first suborbital flight and announced to the nation and to the Congress that the United States is going to send astronauts to the moon and return them safely by the end of the decade. It's like, really? You're really going to do this? Because the gap in technology that existed between that first primitive suborbital flight and what was necessary to go to the moon, to land the astronauts, return them safely, was enormous. We've never, in the history of humankind, undertook a technology development effort of that magnitude before. And it was ultimately successful. Now, Kennedy, about a year later, in 1962, made a speech at Rice University to elaborate a little bit more on why we were going to the moon. And it's probably viewed in the space policy circles as the best speech any president has given on space. So I'm going to play you just a little bit of it because, and then we'll talk a little bit about it, because he lays out his rationale for the moon.
Why some say the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
So he starts off talking about how space is hard, and it is. And it is, and it continues to be very difficult. It's expensive, it's difficult, it's challenging, it's dangerous, but there are great adventures. Kennedy was taking the high road here in his speech, talking about climbing the highest mountain, adventures. But really, historians know, and going back and looking into the record, that Kennedy wasn't all that interested in space. What he was interested in was beating the Soviet Union. And you remember, a number of you, like myself, lived through that time period and remember that who was first in space? It was the Soviet Unions with Sputnik. Who was the first astronaut? It was Yuri Gagarin, a Soviet. Okay, and at that point in time, we were starting to look pretty bad. And so Kennedy was looking for a bold, audacious goal in space that he knew the Russians would struggle with, because this was such a leap in technology and would be so expensive that we would outspend the Russians. Ultimately, as you know, that's also how the Soviet Union fell, and continuing to outspend them on many of their military. So Kennedy set that as a goal, and he packaged it so well. He was such a wonderful speaker, packaged it so well around this flowery language, but it was really about beating the Russians. When that happened, so here's the problem. So when that happened in 1969, of course, Kennedy was gone at that time. Lyndon Johnson, also, who was vice president and then president, was also gone. So we landed on the moon in 1969. The reasons for the space exploration ended because the United States won the space race. Okay? And so very quickly after that, Richard Nixon canceled the Apollo program. There was a total of 6 landings on the moon, but it was very expensive. We were spending of order 5% of the gross national product on NASA in those days. Today, it's more like 0.4% is what is spent, 10 times less. So it was deemed, no longer viable because we had won the battle. So that as a reason to explore space obviously wasn't sustainable. And we backed away and have not been back to space since. If you would have told me, I was in college at in the last Apollo landing in 1972. If you would have told me then that it would be 50 years before we would go exploring again, I would have called you crazy. I think most of us would. But it's coming up on 50 years now. So we continue to search now today in a very different environment. There's no Cold War going on. There's no space race, which is taking place with any other country. So why do we explore space today? And the reasons have to be fundamentally different. So a lot of people have tackled this. Stephen Hawking, for example, has gotten very interested in recent years in space exploration. So here's one quote from Hawking, in which he says, "The situation today is like Europe was before Columbus's voyage. Spreading out into space will completely change our future, but won't solve immediate problems." A couple of interesting things in that quote. Hawking is probably right that when we do become a true space-faring species, when we're permanently in space and we're traveling out into the cosmos, who we are, what we are, our vision, maybe even our biology will change over time. But it's a long-term kind of thing. And those that promote space as, for example, having magic bullets of technology to solve our problems today, that's not correct either. So it's a long-term evolutionary process. We have to be in it for the long haul. Okay? I remember in the 1980s, the mid-1980s, when some folks were advocating for the International Space Station. And I remember a couple of folks going to Congress testifying and claiming that because of the International Space Station and the microgravity environment, we were going to cure cancer. It's like, really? I'm not a cancer biologist, but even I know that can't be true. And so overselling doesn't help as well. So what's the right balance? What's the why of space exploration? And what I want to do is follow an analogy a fellow named Simon Sinek has been using recently. He's a management consultant, really thinks a lot about companies and why they exist. And he has developed this very simple little graphic here in which he says that at the center of companies and what should be their DNA should be this question why they exist. And then only after that, surrounded by the how and what of their company. But at the core, it should be why. Sinek says most companies, very few companies, think in this way. They really don't know why they do what they do, what their purpose is, and really why does the organization exist. And Sinek uses Apple Computer as a counterexample, in which Sinek says that, if Apple were like most other companies, they might sound something like the following in marketing their product. We make great computers. They are beautifully designed and user-friendly. Want to buy one? Well, okay, maybe, sounds all right. But, how's that any different than anybody else? Sinek says Apple approaches the problem differently, fundamentally differently. He says that their approach is something like this. Everything we do, we believe in challenging the status quo. We think differently. The way to challenge the status quo is by making beautifully designed, user-friendly products. We just happen to make great computers. Want to buy one? See the difference? What there is a hint of rebelliousness there, right? A hint of revolution, a hint of Steve Jobs, certainly, in the way he looked at things. We want you to join the rebellion, okay? We're doing something neat. And people who have Macs, and there's probably a number of you in this room, feel that same way. We're sort of rebellious by just buying a Mac, okay? And to operate in that fashion. Imagine now applying this to NASA in the space program. What might this sound like if you were to take that same sort of approach? So here goes. Here's what I think this might sound like. We, NASA, we believe in challenging the status quo. We think differently. We thirst for knowledge on where we came from, our destiny, and if we are alone in the cosmos. We build beautifully designed rockets, telescopes, and tools for exploration. Want to join us in this adventure? Anybody? Yeah. It's a little rebellious, right? It's a little on that cutting edge. This is the way NASA was in the 1960s. In the mid-60s, the average age of the NASA employees was 26 years old. Okay? Today, it's mid-50s. I don't know about you, but as I've aged, I've gotten a little more risk-averse. I'm not, In those days, NASA had no choice but to take risks because there's no technology, okay? Everything had to be developed new. Over time, the agency has gotten much more risk-averse, and frankly, it's more difficult to do those kind of revolutionary things, but it would be nice to be able to revisit it. This sounds a little bit like SpaceX and the way Elon Musk runs his company today. A lot of young people, a lot of excitement there, a lot of risk-taking that's associated with it. So if it works for Apple Computer, why not work for the space program? and just be outright inspirational. We go to space because humans are meant to explore. It's always been true. Always been true. Thousands of years. People want to know what's over that next hill. We are explorers. It's at our core. Countries that have developed great exploration programs have been economically successful, politically successful, and those that have pulled back, and a number of countries that have done so. China, we can think back in the 1400s, eventually collapsed, was invaded. We explore to gain knowledge, to satisfy our curiosity. Space today is that new frontier. It's a simple answer as to why we explore, but it's a powerful one. It's one that really builds on who we are. This is why NASA continuously is ranked as the most popular federal agency in the government versus the IRS, for example. It just doesn't do particularly well in those rankings, but I can't understand why. But so, having talked a little bit about this inspiration and the why, what I want to do now is spend a little bit of time talking about the how, the where, and the what of space exploration. But inspirational is at its heart, and the reason is we want folks like this to be inspired. This is our grandchildren. Kathleen here in the front and myself. This is Kelsey and Jackson at Science and Museum in Indianapolis, where they live, and they're little space explorers here. And I want them to be inspired. I want them to look at the opportunities of going into space or being part of the technology revolution that will result. So how do we explore? I mentioned at the very beginning we've got some new tools. And here's NASA's #1 new tool for exploration. This is the Space Launch System, and the Orion, which is a capsule on top. Looks a little bit, at first glance, like the Saturn V, only it had these solid rocket boosters, which are derived from space shuttle technology. So you get the fairing coming off here, and now you see the Orion capsule built by Lockheed Martin, and the second stage, which is doing a translunar injection. This is not your grandfather's Apollo capsule. This is all modern avionics, better insulation from space radiation, and computer technology at the max. So this vehicle is going to be launched for the first time next year, or a year and a half from now, so I think probably early 2020 now. Its first will be an uncrewed launch, and it will go to the moon. Very first mission is to orbit the moon and return. And then the next launch in 2022 will be a crewed mission with 4 astronauts on board. And once again, it will orbit the moon. So right back and starting that process again. This is NASA's brand new announced lunar exploration campaign strategy. Just came out in the president's budget just about a week and a half ago. It's something that we advocated very strongly during the transition process of looking at opportunities to begin exploring again. And the most immediate opportunity is, in fact, the one of returning to the moon. For the last number of decades, we've been in orbit of the Earth. Of course, the International Space Station has been our workhorse. And now with the Space Launch System, with the Orion, returning to the environment of the moon. I'll show you just in a moment here. A very important piece of new hardware is a new small orbiting platform that will allow the Orion spacecraft to dock and eventually then for landers, both robotic landers and human landers, to return to the surface of the moon during the decade of the 2020s. And certainly Mars remains as that horizon goal, but Mars is very, very difficult, very difficult. It takes 9 months to get there. You have to live off the land immediately. You have to generate your own fuel, your own oxygen, grow your own food. You have to stay there for at least a year, and then another 9 months back. That's a really, really rough trip. Whereas the moon is 3 days away. okay? We can do that. We need to start exploring again, and we can't wait to get to Mars, okay? So we need to do this now. And so that's why the moon makes so much sense. And it's a large body, and it happens to be placed in proximity. So the Orion and the SLS, these so-called Cis-Lunar missions, these are missions that are in the space between the Earth and the Moon. This is an attempt now for astronauts to begin becoming Earth independent. Because right now when the astronauts are aboard the International Space Station, virtually every minute is programmed. They're constantly in contact with ground control, okay? That doesn't work very well. Look what happened to Mark Watney, on Mars, okay? He wasn't getting much help, right? He had to grow those potatoes. He had to figure this all out. He had something in his gizzard that he had to pull out and repair himself. And so, that is the way that space exploration is going to be from here on in. We're not going to be in constant contact. And so there are a number of things that we're hoping to see developed during these beginnings of human space flight in deep space once again. The radiation environment is very important to understand and protect the astronaut. Both radiation from the sun and from galactic cosmic rays are very harmful. We still need some technology solutions, higher bandwidth communications using lasers, what's called optical communications. More self-sufficiency, as I mentioned before. A new mode of operations that does not asking ground control, mother may I, every time you want to do something, okay? So the capabilities, we have to improve our recycling of life support systems, food, repair, and of course, beginning, my favorite, a science program in the vicinity of the moon that I will be telling you a little bit more about. So this is what Orion looks like. This is the breakdown of it. This was built by Lockheed Martin in my state of Colorado, down in Denver. And you see the capsule here. This is an escape system for early on. So this is much safer than the space shuttle, which did not have such an escape if there were problems on the launch pad or shortly after launch. And then there's a service module behind here. This is built by the European Space Agency. So already you see a difference between Apollo and today we have a collaboration with the other large space agency in the world today, ESA. And we're working together, and I think that's going to expand with other countries as that goes forward for the future. So as I said at the beginning, a crew of 4 initially, maybe an upgrade to 6. And the next stage of this, which NASA is planning, was in the budget, in the president's budget at least, for next year, is something called a deep space gateway. And here's an artist version. This is a pretty picture. This is a new artist version that Lockheed Martin has produced. They've allowed me to share it with you today. You can see it in orbit of the moon. It's not gigantic like the International Space Station. This is going to be kept modest in size. So here's Orion down over here. It's docked to the Habitat module. And what's different about this deep space gateway or lunar orbit platform, as it's also called, is this module right over here. This is a propulsion module. And so this is actually a spaceship. This is not a station like the ISS, which is frozen in one orbit. This is movable. It can be in low lunar orbit, it can be high lunar orbit, even in what's these regions called Lagrange points, which are balance points in gravity between the Earth and the moon. And one of those points is a particularly favorable one because it sits above the Lunar Farside and gives astronauts an opportunity to be viewing the Lunar Farside and still be in contact with Earth at the same time. So it's a favorite place of mine, as I'm going to talk about in a few minutes, because it opens up the Lunar Farside for investigation. So this is one concept of what the gateway would look like. All of them, though, have a propulsion system. And in that launch I was telling you about in 2022, this module, the propulsion module, will be the first one launched. So we're just a few years away from that. As I alluded to, this is going to open up a lot of new lunar science, and particularly from the far side of the moon. We've never been to the far side. The moon is what's called tidally locked. So one side is always facing the Earth. That's the side we see. It's the man in the moon, right? We never see the far side. But the far side has many interesting and different characteristics. So a deep space gateway, for example, will serve as a communication relay between assets, landers, rovers on the far side and the Earth, because you have to have a relay satellite in order to get communications back. It will do something that I will describe in a few minutes called surface telerobotics. That's astronauts operating rovers on the surface of the moon and doing construction tasks, doing geological investigations. Radio astronomy, which is my favorite, that's my topic over here with a low frequency radio telescope. Understand the radiation environment in deep space, and then also returning samples from some of the oldest impact craters in the solar system on the moon. So lots and lots of science to be done that's really exciting. So obviously, where do we want to explore? I think it's the Lunar Farside, right? So it's because, you know, we've never been there. This is amazing. This is amazing. It's the closest body to us in the solar system. We've never had a lander. We've never had robotic vehicles. We've never had humans on the far side. We know more about parts of Mars than we do the far side of the moon. Yet, there's some really interesting features. This is a topographic map. So it shows you the heights of things. So right down over here in purple, this is a low region. It's a large crater. And high mountains are in red and white over here. So it's color-coded that way to show you the topographic features. So the far side of the moon represents literally an entirely new, unexplored world. Okay, you want to go exploring, where do we go? There it is, right in our backyard. Never been there, never touched it. And it's going to open up all the opportunities we need to really push us, to push technologies that have humans and robots working together. So unlike the 1960s, where you had astronauts like Jack Schmitt out there with a shovel, digging in the dirt, collecting things, using traditional field geology techniques, this next generation of explorers are going to be working together with robots, with rovers, who are going to be commanded by astronauts in real time and as a team. So developing those strategies is going to be important not only for the moon, but then how we're going to explore other areas of the solar system, asteroids and Mars. This depression that you see over here, this is called the South Pole Aitken Basin. This is the largest, deepest, and oldest impact basin in the inner solar system. It was formed over 4 billion years ago, okay? The Earth-Moon system itself is 4.5 billion years ago. What's interesting about this basin, we think it has many of the secrets about the evolution of the Earth-Moon system that we can't obtain from the Earth, because in the case of the Earth, as we know, the Earth has changed a lot, changes all the time, wind erosion, soil, ocean, rains, all of those things. The moon, no. The moon has stayed pretty much the same because it has no atmosphere. And so the moon is a kind of witness plate to the evolution of the Earth-Moon system. And one of the things that's particularly exciting is, you know, when this South Pole Aitken Basin formed and some subsequent impacts, this was about the same time that life was first beginning to emerge on the Earth, first single-cell life. These same kind of craters, the kind of impacts that made these craters were happening on the Earth at the same time. All of that history has been wiped out. But did those crater impacts play a key role in the formation of life? Did they bring elements of life to the Earth? Or did they at least stir the pot, bringing in heat and energy to create? Of course, we don't know. We don't know how life formed. But by studying the moon, we have a unique resource right in our backyard to go back and revisit our history of how the inner solar system formed. And then finally, I'm interested, as I mentioned before, because what we want to do is place low-frequency radio telescopes on the far side of the moon, because the far side is the only truly radio-quiet environment in the inner solar system. We are interested in operating telescopes below the FM band, so below about 80 megahertz or so, and the Earth's surface is terribly polluted, coupled with the ionosphere, so that it's polluted with radio frequency interference, and so you can't do those observations easily on the Earth. The far side blocks the emissions from the Earth and gives us a true radio-quiet environment to allow us the first time to use radio waves to explore the epic formation of the first stars and galaxies in the universe. It's a pretty important topic. So going back to, we always ask where we came from, how life did. I mean, going back to the very first galaxies and stars is something that we don't have a good handle on today. So we can do that. So my colleague, David Kring, at the Lunar and Planetary Institute, he's very high on the South Pole Lake and Basin, but particularly the basin is huge. So there's another impact crater here called the Schrödinger impact crater. And this was made millions of years later, after the original basin was formed, and it upwelled this material in here from the subsurface layers. David thinks that we can land on the surface here with a rover and literally pick up rocks off the surface that are 4 billion years old, okay? And bring them back and analyze them, understand that evolutionary history. And as it turns out, we've studied also parts of this crater and done our modeling. It's going to be quiet enough for us to put our low-frequency radio telescopes. This imaging was done from NASA's Lunar Reconnaissance Orbiter and reconstructed to put together kind of a mini voyage of what a first mission to the Schrödinger impact basin might look like. So David zooms in here in just a moment. This was viewed by the National Academy of Sciences in what's called the Planetary Sciences Decadal Survey as one of the top priorities for planetary science in this decade, is to bring back samples from areas like this on the moon. So you can see even from orbiting, you get a pretty good glimpse of the moon in this crater in here. Okay. So, and then, as I mentioned before, we are interested in deploying our low-frequency radio telescopes down here. This is kind of a cartoon picture of a rover deploying a piece of Kapton film where we embed low-frequency dipole antennas that then we electronically sync up together to observe these very weak low-frequency signals from the early universe. So, and this also was represented by the National Academy as one of the top priorities. Astronomers call this cosmic dawn, okay? So the first stars turning on in the early universe. So here we have an opportunity to do two things, very different: planetary science or lunar science and astrophysics and cosmology from the moon with one mission from the far side. All right, well, you've already seen a hint of some of the tools to be used here. And of course, robots have been employed in the space program for many years. The workhorse today is NASA's Curiosity rover, currently on Mars. But it operates in a challenging environment because Mars, the return signal takes 8 to 40 minutes, depending upon the orientation of the Earth and Mars orbit. And so you send the command, you have to wait, it moves, a few centimeters or a meter, and doesn't make a lot of progress, okay? What we're talking about doing is being able to teleoperate rovers when you have astronauts that are there in real time and move them along and do real-time operations. You also got Robonaut on the International Space Station. Poor Robonaut has been out of service for a while, and he's going to come back down for repairs, but he was built to help the astronauts. Of course, the idea of robots working in space goes way back, okay? It goes way back. Lots of robots in movies. Let me show you one of my favorite movies from the mid-1950s, Forbidden Planet. And Robbie the robot, one of the first robots that was in there. We're going to need to turn this up. Walter Pigeon. I want that robot. That's my idea of a functional robot. Cook my meals and drive my atomic car. So, you know, I'm ready for that. But, you know, that was sort of the view of a robot for a long time. And most people's view, autonomous sort of object, just does their own thing, serves humans, you know, in this way. That's really not the way space robotics is going to work today. It's also not going to hopefully not going to work the way it was portrayed here from the day the Earth stood still, with Gort here, who was threatening to destroy the world if we didn't stop dropping our atomic bombs on each other. And then, of course, probably the best known robots today.
What mission? What are you talking about? I've just about had enough of you. Go that way. You'll be malfunctioning within a day, you nearsighted scrap pile. And don't let me catch you following me, begging for help, because you won't get it.
Again, autonomous creatures, own personality. They're like sort of semi-human. But once again, that's not a practical way to look at how robots will work I think in the future, certainly in assisting in space. So what I want to do is tell you a little bit about some of the work that my colleagues and I are doing in this area of surface telerobotics. And here's a roadmap we put together a few years ago, particularly my colleague Terry Fong at NASA Ames, who has led much of this early effort, to work on control of rover vehicles from orbit by astronauts. We started off with some ground analogs, and then a few years ago we actually ran the first tests aboard the International Space Station. We had astronauts aboard the space station controlling independently and directly rovers on the Earth at NASA Ames Research Center. And having progressed very nicely there, we're ready now to start looking at employing this with lunar orbit and the Deep Space Gateway. And then especially will be relevant for Mars, because the first Mars missions will probably also be orbiting missions. And astronauts can use robots as effectively avatars to do real-time exploration on the surface. So let me show you our robot here. It doesn't look much like R2-D2, but this is K10 and has several different sets of cameras, and including dual cameras up here, a LiDAR system for mapping the terrain as it moves around. And here is, this is at the what's called the Roverscape at NASA Ames. So this is a simulation of the moon here in this case. And here's an actual operation. I'm going to turn on this part of the video here. This is astronaut Luca Parmentano from Italy operating our K-10 rover aboard the International Space Station. And you can see the interface up over here. This is what's moving. Luca's very focused, so his head's not moving very much here, but he's very focused on the interface, which was what Terry Fong and his colleagues built. And you can see several different things. First of all, what we're doing is we're deploying some of this capped-on film that I talked about before. My students and I built the deployer system on the end here. And so it's not a functional radio telescope, but it's just an example of what this might look like. And Luca up over here is, he's looking at the terrain. So the LiDAR is mapping the terrain. You can see that those boulders were identified. And so the astronaut is maneuvering the vehicle around those obstacles. We also had, the bandwidth wasn't high enough to give us real-time video, but we could do regular stills, so every few seconds or so, still pictures, and move this through. This is the first time anyone has controlled a rover from space on a planetary body. Now, it turns out that planetary body was the Earth, but that's all right. You know, it still demonstrated the technique of what we could do, and ESA followed that up about a year or so later with a similar experiment. So as part of what we did is, we deployed multiple versions of these polymi, because what we would like to do is have a number of radio antennas laid out in a configuration like a Y that we would then electronically phase up. And then go back and inspect to make sure that there's no tears, there's no faults associated with the radio telescope. So we went through all of those, and here's a summary slide that shows the 3 missions, that is the 3 sessions, survey, deploy, and inspect with 3 different astronauts. Now, I found this pretty amazing, because this was my first opportunity to work with crew on the space station, because we had, each session was only 2.5 hours altogether. That's all the astronaut time. Astronaut time, crew time is very, very valuable. They had to go through training, because we had to take them through training before we ran the experiment. So it was training plus running the experiment plus assessing in that period of time. These are very smart people, okay? And they did a great job and demonstrated to us that this human-robot team interaction performed well and very safely. There was great situational awareness throughout. The rover utilization was reasonable. Any crew interventions were successful. And very importantly, the crew workload was low. They found they were able to handle this very easily. And that's great, because what we would like to do is, both on the moon and eventually at Mars, is to have crew operating multiple rovers at the same time, to be able to do a number of different related tasks. And one of the rovers sees something interesting, they shout out to the astronauts, hey, this is interesting over here, come and take a look at this. So this is very encouraging, and we have published these results. Here's a fun project, though, that I've done at Colorado with my students, because telerobotics also lends itself very well to working with students. These are 2 undergraduate students in my lab, Ben and Matt, and they're both engineering students. And what we did is we built our own little telerobotic rover here for the purposes of understanding effects due to frame rate and bandwidth on the ability to identify targets of exploration. In this case, it was very simple. We had just these colored rocks that we put out here with lettering on. And then we had a student operator in a tent, so he could not see directly the rover. He could only control it from the interface, again, like the astronauts did aboard the International Space Station. And we experimentally determined what the minimum frame rate was going to be for the video in order for the exploration to be successful. And we found out that if you drop much below 5 frames per second, then the accuracy of the exploration dropped off as well. So this is good information to have. We have sort of a baseline of what the minimum bandwidth needs to be for Orion and the Deep Space Gateway in moving forward. And again, it's a great project. These students led this work, and we've published a paper on this, and they're, in fact, in 2 weeks presenting at an IEEE aerospace conference in Big Sky, Montana. I'm sure they're going to do some skiing along the way. So here's another approach that we've taken, our group, recently that we're very excited about. And that is, we're continuing to work with real rovers, but we're also moving in the virtual reality simulations. This is working with a Ph.D. student in computer science and a professor student of computer science, also at the University of Colorado. And what we've done now is we have placed a simulated rover onto a simulated lunar landscape. And you saw the 2 controllers that we had over here. So what we have begun to do is to be able to take these simulations to the next step and use this as a playground, if you will, to understand what some of the issues are going to be to operate these rovers. So we can control the physics, we can control the gravity, the dust environment, the glare that's there, and the glare is very different on the moon than it is on the Earth without any atmosphere. And you can do this both with the rover, sort of a third person looking from a distance, and then you'll see just a moment we can switch the scene to what an astronaut who would be in orbit controlling this rover would see out of the rover's camera. So this will switch over here in just a moment. Get some idea. So here we go, the controller going off. So here's what you would see with the rover's camera. We degraded the image a little bit here, made it a little grainy to sort of illustrate what this might look like. Here again, we can do experiments on bandwidth, color, and effectiveness. We'll also be looking at simulating construction tasks and assembly tasks of our low frequency. So we've got a new set of tools here to be able to work with on this. We're partnering with our colleagues at Lockheed Martin and part of my center at Colorado is working on this. So another way of being able to explore this. So where we're going, once again, just to revisit this is an exploration strategy, an evolutionary strategy for exploration that started in Earth orbit, the International Space Station, going to the moon, and then off to Mars. That is what's going to make a sustainable space program. But you also add new elements into this about how we explore, and that is the private sector. So here's a video from SpaceX of what Elon Musk is calling the BFR, okay? Now, some say that means Big Falcon Rocket. I'll let you, this is Elon Musk, so you can interpret it what you will. But this is a big rocket, and reusability is the key for SpaceX and what he wants to do. I mean, Musk has big plans, about wanting to send a crew of 1,000 people to Mars. Okay, we need to get some people back to the moon first, and at least one person to Mars. But he's ambitious. Nothing wrong with that. To look at these kind of bold ideas, and this particular rocket has like 40 engines associated with it, all have to run simultaneously, and he recovers the first stage, as he's done successfully a number of times now. This is a cartoon picture of that. So he reignites the first stage engine, sends it back to the vicinity of the launch pad, and lands it, because one of the most expensive things are the engines here. And so being able to recover the engines and refurbish them, he believes in his model will be cost effective and will make access to space cheaper than it has been previously. So here's the idea. It comes back around. Now it's not going to be this fast. We're not going to turn it around quite that quickly, but it's been speeded up here just a little bit. But you get the idea that you refurbish the engines, reuse them, and in this case he's got 2 of these, because what he's doing is refueling now the crewed spaceship with a second one that's just it just contains extra fuel, then igniting the rocket and sending it off to Mars, like Elon did with his red Roadster when he launched the Falcon Heavy. In this case, again, you've got a crewed mission shown in this illustration. And it's a lot easier to do these videos in PowerPoint than actually do this in real life. Let me just to tell you this, it's easy to make videos. So there's a lot more development that would be necessary to actually make this happen. But again, it's exciting because the private sector now has the ability to be able to do things that only a country was able to do. It took, during the Apollo mission, the resources of the wealthiest country in the world, and a lot of resources, to get us to the moon. Now you can have individual companies sending unmanned payloads to the moon. We're getting ready to have several companies do that, and even ambitions to do things like, go to Mars. So this would be, his vehicle, his version of this. Lockheed Martin has another version that they put together of a similar mission that they're looking at as well. Jeff Bezos' company's Blue Origin is right behind, and also building vehicles, and there they are at Mars. So that's exciting, that's new. And that will help to develop what we think something different than the 1960s, a sustainable space program, because what we didn't have in the 1960s was sustainability. It ended. It ended because it was driven by political motives, not by a long-term view, not by a number of different countries and companies seeing business models of not only just exploring space, but money to be made in space. One of the things I hear all the time is our argument that people ask me the question, should we go to the moon or Mars? I say, wrong question. It's the moon and Mars. And here's why that's different, even different than 10 years ago. Because now the moon is accessible by private companies, okay? And partnering, public-private partnerships with companies like SpaceX, Lockheed Martin, United Launch Alliance, Blue Origin. Now, they are driven by what they see are some business opportunities. The federal government is driven by developing an expertise onto the surface of planets and being able to go to the next step. By partnering together, we have a way of developing facilities on the moon a lot more cheaply than we could even a few years ago, and not be totally dependent on a big federal government program. That does free up NASA to be able to focus on things only NASA can do, and despite Elon Musk's video, that's Mars, okay? Because Mars is hard. It's really, really, really hard to be able to get there. But a sustainable space program is one that doesn't have a single destination. It has a strategy to explore beyond and to continue that exploration outward into the solar system. Mars is very interesting because it may have had life. We think it had an ocean at one time, and maybe primitive life started. We want to explore that. But there are other also very fascinating, very different places to look for life in the solar system. Europa, one of the moons of Jupiter, has an ocean of water underneath a frozen cap, which is probably about 10 kilometers or so in thickness. and a whole ocean of water. Might life have formed in that environment? We know life began in the oceans on the Earth. Very different place to look for life than on Mars. Mars is very dry today. And so there are water spouts coming out of Europa, which we've seen some orbit. So here's a couple of missions that NASA's looking at on orbiter called the Europa Clipper, sending it to Europa to begin this, and then maybe at some point in the future, a lander to drill down through one of those water spouts and look for biogenic material that might be emerging. And after that, continuing outward, I mean, eventually beyond the solar system, we have discovered in the last 10 years 3,500 planets around other star systems. 20 years ago, that number was 0, okay? And so that has been done with new telescopes like the Kepler Space Telescope. And we find that stars of all types have planets. And many of those stars are around what are called red dwarfs or M-dwarf systems, that the planets are nearby the stars, they're close to stars, but these stars also are very active. They have flares. This is a highly stylized view of solar flares and what's called a coronal mass ejection. And that could be enough to wipe out the atmosphere of a planet. We need to know that before we think, get too seriously about any particular one of these. But we can explore that now with things like using our low-frequency radio telescope on the Lunar Farside surface, because it also will allow us to probe literally the weather in these systems, because these storms emit low-frequency radio emission. And so we can actually probe the weather right now. We don't have to wait to send a spaceship. We can do that right now. And next generation large space telescopes using things like a star shade to help us actually image these exoplanets. That's all coming up in the next few years. And then who knows, maybe in the next century, we get our own interstellar starship. We got a little bit of technology to be ready for that. But it's pretty exciting overall. So just a few closing thoughts, and I could go on for another couple hours, they wouldn't be much, but I think we need to draw it to a close. It's getting back to, what is a well-designed and well-executed, inspirational, sustainable space program? It has to have all of those things associated with it. So it's got to drive advances in science and technology. It has got to expand opportunities for everyone, because space now is just not an American thing like it was in the 1960s. All countries, all civilizations, all peoples now can participate and should be participating in space exploration. That's what makes it exciting, and it's going to enhance and expand knowledge, education, innovation. No question about economic vitality. I mean, again, you've got some big and small companies right now that are plowing millions of dollars. In the case of Jeff Bezos, he cashes out $1 billion a year of Amazon stock and puts it into Blue Origin. He's taken no government money at this stage, okay? Don't you wish you could do that? That would be fun. Some people can. Advance our understanding of the Earth and develop technologies, but it all comes back to that why. We've got to feel secure about why we explore. And if this inspirational idea, economic development, the associated with it, if that's drive us, let's stick with it and go. Then talking about the how and the what, using new things like public-private partnerships is exciting. And I think the bottom line in all of this is, with space the way it is today, with the technology, with the opportunities, there's room for everyone to be a participant in space exploration. Thank you. Happy to take some questions. Let's start right off over here in front.
In space, you don't have any friction, or I don't think you have a whole lot of friction. What's the fastest you can actually travel? Well,
you're limited by the speed of light. And so that's the limit of what you can travel at. So, for example, the nearest star system to us, just the nearest star system, is about 4.4 light years away. So if you could travel near the speed of light, it would still take 4 years to get there. So space is really big. The Milky Way galaxy is 100,000 light years end to end. That's just our galaxy alone. So it's gigantic. There's a lot of empty space. The galaxy is mostly empty space, and you get the few stars that are there. So interstellar travel, unlike the movies and Star Trek, you know, where you go to a new planet every week, that's probably not going to be the way to do it. Okay, so I'm going to make it easy on you. We'll start right here, and then we'll work our way back.
You mentioned stir the pot,
Yeah.
and I'd like to ask, it was mentioned on public television a few months ago that the thinking is now that there's a black hole at the center of every galaxy.
Yes.
Do you see the black hole as a giant electromagnetic recycling center?
Well, you know, the black hole, I think we sometimes have a misconception of what black holes are. And you're absolutely right. We astronomers now, we believe there is a black hole at the center of every galaxy, including our own. There's a 4 million solar mass black hole at the center of the Milky Way galaxy. But it's not going to gobble up the rest of the Milky Way. When you get beyond being very close to the black hole, the gravity drops down to a normal amount that it would have for any. It's only very close to the black hole that the gravity is much more intense. So it doesn't sweep everything up. It's not going to eat the Milky Way. But occasionally things come close enough to it that a star or a cloud of gas falls in, and we see a hiccup. We see a burp come out of the center of these galaxies, including our own Milky Way. And galaxies burp, you know, because they have some indigestion from the meal that they just had. And it's actually what happens is it creates an accretion disk, heats up, and it emits X-rays, it emits radio waves, and we see that.
Time for one more question.
Okay, who is really excited to ask that? There's a young man right behind you here who looks really excited.
You mentioned the decadal survey.
Yes.
And Europa Clipper, which is on that list. They put you in charge. What mission are you going to pick off that list? There's a Titan mission, I know, that the terrestrial planet finder is a pretty interesting one. What would you pick if they put you in charge to see fly?
A South Pole Lake and Basin mission back to the far side. Are you surprised by that? I mean, no one would be surprised. When I was on the transition team, there were some people who said, "Oh, there's Jack Burns, is that moon guy is on there." You know, so you know, we're going to send NASA back to the moon. You bet. Yeah, sure.
And on that note, let's thank Jack.